Okay, let's see, I'm Jack Dongera. I work at the University of Tennessee, Oak Ridge National Laboratory in the University of Manchester. And I'd like to talk about give you an overview of high performance computing. I can figure out how to change the slides. There it is. Okay, so this is the state of supercomputing here in 2020. This is based on the top 500 list. And one thing you should notice is that all of the machines on the top 500 have a petaflop of greater performance. And that was really established about a year and a half ago, I think, was when we first reached that point. So all the machines on the top 500 have had performance greater than 1 petaflop for the benchmark. There are 3 architectural lanes that we see for the machines on the top 500. So think about a supercomputer and how are you going to build a supercomputer? One model of that, or one of the lanes, is to use commodity processors. That is, just take a bunch of Intel processors, connect them together with some kind of interconnect, maybe gigabit Ethernet, and we're going to call that a supercomputer. And then we run applications on that using MPI across that machine. The second architecture is to use those same commodity processors, but put them together with accelerators. Accelerators that'll boost the floating point potential. We sometimes refer to these accelerators as GPUs. So commodity processors plus accelerators are used in 149 systems of the 500 machines. And it's interesting to note that 142 of those systems use NVIDIA accelerators. 4 of those use Intel Xeon 5 accelerators, and 4 use some other combinations. And then there's one machine of the 149 that have a combination of NVIDIA and Intel processors, sort of a Frankenstein kind of a machine, if you will. And the third architecture is to use lightweight cores. That is, there are processors that have been built that have very simple processors. The IBM Blue Gene is an example of a chip that uses very lightweight processors. Those processors don't have the same sophistication in terms of cache management, in terms of instruction look ahead, in terms of prefetching things. They're very simple in nature, as opposed to, let's say, a full Intel processor. And the other examples would be the early versions of the Phi processor, the Chinese Tahoe Lite, and even the ARM processors to some extent exhibit this lightweight core nature. So those are the 3 architectures that we see, and we'll see them pop up in the top 10 list, in fact, as architectural models. China is a top consumer and producer of machines in the top 500 list. And this is something relatively recent. In the last 5 or 10 years, China has really been very aggressive in terms of producing machines and to have machines in various installations in China. That's true for the top 500, but if we narrow the focus and look at, let's say, the top 50 machines, China really hasn't had the same impact in those 50 most powerful machines. And I'll give more details on that. It's interesting that high performance computing is worldwide, of course. There's new markets. When you take a look at the top 500 machines and look at where they're deployed, what we see or observe is that 50% of the machines, a little bit greater than 50%, are actually used in industry. So industry gets it. Industry understands that these computers, supercomputers, provide some kind of competitive advantage for them, and they're willing to make an investment to use those machines to help with the production of whatever they're making. Intel is very impressive in the sense that if you take a look at Intel processors and look at the top 500 list, 92% of the machines use Intel processors. That's a stunning achievement, I would say. And AMD has 4%. So when you add those up, you get 96% of the machines on the top 500 list use x86 instruction set. So that's a big achievement, I would say, for that. Well, it'd be interesting to see how if that continues into the future. And what we have is exascale on the horizon. There's many projects in many regions looking at exascale, trying to understand, can we in fact build an exascale machine? How will it be built? And people are willing to make an investment in getting to that point to help drive science. Science today is driven by simulation, and the exascale machines, of course, are the things which fuel that simulation, and to some extent, you could say, drive science today. Okay, we're going to take a look at some of the top 500 list here. This is a list that's been put together since 1993. This is the 56th edition of the top 500 list. We're looking at the 500 fastest, most powerful computers in the world, and we're going to measure them against the benchmark. And we can talk about the benchmark for better or worse. It's the LINPACK benchmark. LINPACK says we're going to solve this system of equations, AX equals B. The ground rules for solving it is you're going to be given a dense matrix. There's no, think of it as a matrix which has has no zero elements in it. The ground rules specify that you must use Gaussian elimination with partial pivoting. It says you have to use 64-bit floating point precision to solve the problem, and you have to compute a solution which is accurate up to a certain point given the floating point representation. So this list is updated twice a year. It's updated in November as it was yesterday, and it'll also be updated at a meeting that's usually held in Germany in June at the ISC meeting. If you take a look at what happens as you run your problem for different problem sizes, the rate of execution increases until we get to some asymptotic rate. And we're really trying to capture the asymptotic rate. So you want to solve a large matrix problem on your machine so you can drive up that performance to get to that asymptotic rate. And I think the biggest matrix that was solved is a matrix of size 21 million. So that's a dense matrix of size 21 million. And that was done on the Japanese machine, the Fugaku system, that achieved the highest performance. So all the data from the top 500 is contained in that website. You can go back and look at it. It's contained from the early days until today. This, in some sense, is a snapshot, if you will, of the supercomputers ranging from 1993 until today. And what we're looking at here is the top 500 list. We're looking at the sum of the top 500 list. That's the blue line that's charted there. Today, we have 2.4 exaflops if you add up the sum of the 500 machines that are on the list. That's an Excel sheet computation of just adding up the numbers. The number one machine on the list comes in at 442 petaflops, and that's the Japanese machine, Fugaku, which has a very impressive architecture and has very impressive performance characteristics. And the guy at the bottom of the list that just made it on the list is at 1.3 petaflops. So there again is the bar to get on the top 500 list, at least in November of 2020. And you could see the bracketing there that's occurred between the number one machine and the number 500 machine. And you could look back over time. When you look back over time, you know, if I go back to the number one machine in 1993, that was a thinking machines, a CM5 with 1,000 processors. That was at Los Alamos National Laboratory and used to carry out classified computations about nuclear weapons production. So that was done in 1993. It's interesting to note the laptop I'm using to give this presentation is a Mac. And when I run the benchmark on this machine, of course, you can run the benchmark on any machine. When I run it on this machine and use all the cores, I get 166 gigaflops for my laptop, which is quite stunning. You know, that would have been a machine on the top 500 list that would have exceeded the capability of that thinking machines back in 1993 at Los Alamos National Laboratory. So very impressive gains have been made, of course, relying on Moore's law, Dennard scaling, and algorithm improvements that have made to various things over time. This is a projection.
Jack, I'm just going to jump in here to let people know there's a Q&A button at the bottom of the screen. And if they want to ask their questions, they should just click on that button and there's a space to ask questions. Okay?
Yes, I should have said that at the beginning. Thank you. So please ask your questions and we'll deal with them maybe in real time, but certainly at the end of the talk. Let's see, where was I? This is the performance graph here. We're plotting the sum, the number 1, the number 10, and the number 100 machine. And you could see there's some trend lines here that have been put on, and the trend lines are showing that the machines have not really kept up with that trend in some sense, deviating quite a bit. And that's caused by a number of things, perhaps because of a downturn in the economy in 2007, perhaps because of Moore's law, perhaps because the COVID. There's a number of reasons I think we can give to that scenario. But just to take a look at this, back in 1997, we had the first machine to reach a teraflop. That was the machine that was at Sandia National Laboratory. It was called the ASCII Red machine, a very impressive machine for its time. About 11 years later, there was a machine at Los Alamos called Roadrunner, which achieved a petaflop in terms of performance. So 10 to the 15 operations on the benchmark. You could see was slightly ahead of the curve there for its projection. And if we look further out, we might say that we should have reached an exaflop about today in terms of where things have been and where the projection might lead us. In fact, China has said that they would reach an exaflop this year in 2020 or 2021. So they haven't reached it, as far as I know, in 2020. So maybe next year they'll reach it. The US has a number of efforts ongoing to reach exaflop, and the US claims through the Department of Energy efforts that they're going to reach an exaflop in 2021. So next year, I would expect to see an exaflop machine in the US at Oak Ridge National Laboratory. This is a more pessimistic view of that. I've shortened the list here, or shortened the timeline from 2013 and then projecting out. And this projection here says that we reach an exaflop in 2023, sometime in 2023. So it's a couple of years difference than what we might actually achieve. So it's just a prediction. It'd be interesting to see what's going to happen. My feeling is that the DOE efforts will produce an exaflop machine next year, and I'll talk more about that in a moment. This is the top 10 list. So this is looking at the 10 fastest machines. So the way to read this here, the guy at the top is the number 1 machine. Whoops, the number 1 machine. That was at the Riken Center for Computational Science. It's a computer that's called Fugaku. It's based on an ARM processor that Fujitsu made. It has the architecture is called an A64FX. That chip has 48 cores. It's running at 2.2 gigahertz, and they have a specialized interconnect that was made by Fujitsu called the Tofu D interconnect. It's in Japan. It has 7 million cores in it. So if you're going to program this machine, you need to orchestrate those 7 million cores to carry out a computation. It does not have an accelerator. It uses, it has a vector architecture, so it can issue vector instructions, but it is not an accelerated machine. There's no attached processor. There's no processor which you have to hand off the floating point computations to. Everything is done inside the processors themselves. That machine ran the benchmark at 442 petaflops, which reached 82% of the theoretical peak performance. Quite impressive. It has about 30 megawatts of power under load. So running the benchmark, it consumed 30 megawatts of power, and that gives rise to an efficiency of roughly 15 gigaflops per watt. So 15 gigaflops per watt is quite impressive. You want that number to be as high as possible. So just looking down the list, we see a number of things. First, let me just point out there are 3 new machines on the list this time. So this NVIDIA Corporation machine, Selene, is a machine that's at NVIDIA, which is used internally at the moment. And it's a very impressive machine with 500,000 cores. It reached 63 petaflops. It uses the new NVIDIA Ampere processor, which has 108 cores in it. And it uses a Mellanox interconnect. And again, you could see it's achieved 80% of the theoretical peak performance. Again, a very high number for that. Another machine is this machine in Germany, Joules, at the Lec Computing Center. It's a machine from Bull. 500,000 roughly is the number of cores. It uses, again, the NVIDIA Ampere processor to boost the performance. It reached 62% of its theoretical peak performance. And the last in the top 10 is this new machine from Saudi Aramco. It's a Cray-based system, uses Intel parts as well as NVIDIA's previous chip, the Tesla V100 chip, to gain its performance. So the top 500 list has a combination of machines. Many of them are accelerated. You could see them. I've highlighted it in red here, the machines that use the accelerators. Those are mainly coming from NVIDIA. Some are homegrown, so the Sunway Tahoe Light has their own kind of acceleration, as well as the Tianhe 2A, which uses a Chinese accelerator in its production. So that's the top 10 list. They're machines which have lightweight cores, I'll say. That's the ARM processor. And then a machine back here at the University of Texas, Austin, uses just Intel processors. So again, just putting together a bunch of commodity processors with a high performance switch and making that into a supercomputer. If we take a look at what's happened in terms of countries, this graph here is called a tree graph. It shows the 500 machines. Each of the systems is a rectangle. There are 500 rectangles here, and they're organized by country. And the area of a rectangle, or the power of a computer, is represented by the area of the rectangle. So the most powerful machine here is this Fugaku system and has the largest area. The second machine is this machine at Oak Ridge National Lab Summit, and then followed by the machine at Lawrence Livermore, and then the Chinese machine, the Sunway machine. So you can just roughly see that the US has, US, Japan, and China has roughly a third each, sorry, roughly 25% each of the performance on the top 500 list. In terms of systems, China has the most systems on the top 500 list. They have 209. So just looking at this tree graph, you see many small systems in China. The US has 110 systems. They're basically larger systems in the list, giving rise to roughly the same performance characteristics as China. So China has 42% of the systems, the US has 22, and Japan has 7% of the systems. But if you take a look at performance and add up that together, aggregate, US has 27% of the performance, Japan 24%, and China has 23%. And then the other countries round out the list there. In terms of producers, China is the greatest producer of supercomputers today, followed by the US. This is charting the over time. So these are machines manufactured in China. They may be using US parts, but they're manufactured in China. So again, you see China has the majority. That has a slight downtick in China. So they're producing less machines than they did last time. US has more machines. They're producing more machines than last time. Europe is producing some machines as well as Japan. This chart here gives a feel for the accelerators used over time, and they're color coded to show where the accelerators are. Just scanning the list here, you see NVIDIA is the major player in terms of the number of accelerators used on the top 500 list today. They've grown quite steadily over time. The newest accelerator, Ampere, is this small wedge at the top, followed by the Volta, which is their bread and butter today, followed by older processors from the NVIDIA family, and then Xeon Phi are other machines that are in the list, which are considered to be accelerators, and then a few scattered other. But NVIDIA has the dominant characteristic for accelerators today. If we take a look at the top 500 list and plot the performance of the machines, you get a graph which looks something like this hockey stick, where we have a few machines at the top, and then this long tail of high performance computing, the soft underbelly, if you will, of the top 500 machines, where we have a peak. The number 500 500 machine has a performance of 1.3 petaflops. And of course, the top one is about 440 petaflops. So you see that wide range. If we take a look at the top 50 machines, you know, it imitates that hockey stick effect, but we can see that the top 50 machines here really consume 60% of the total performance of all of the 500 machines. So it really is top weighted. In fact, those top 10 machines consume quite a large percent. I think it was 40% of the top 500 performance in effect. So things are really weighted at the top end of the list, as you might expect. Looking at the top 50 machines, the US has the largest share there, 32%. Japan is number 2 with 20% of the systems, and France and Germany come in and round that off. And China comes in at only 4% of the top 50 machines. In terms of the vendors, HPE Cray has the largest share at 48%. Altos or Bull, a French company, has 14%. And then IBM and Fujitsu round that out with 14 and 12% respectively. The Fugaku system, the #1 machine, quite impressive. It's made from an ARM chip that was specialized for this process. Fujitsu makes that, produces that chip. It has 48 cores, which are used for compute. There are a couple other cores which the operating system use or maintain. It's a new design, a new core design here. It's a vector architecture, 64-bit ecosystem. It uses a very impressive interconnect called Tofu. Each of these chips produce about 3.4 teraflops of theoretical peak performance using 64-bit arithmetic. It's capable of doing 16-bit, 32 or 64-bit floating point arithmetic. Can also do integers down to 1-bit arithmetic on those chips. It has on-package memory. So this is the only memory it has. The HBM2 memory on chip is there, and it has a very impressive bandwidth. So the bandwidth from that memory into the processor is quite striking when compared to the floating point rate. So think of it like this. This is bytes per second per floating point operations per second. So bytes to flops, you want that number to be as high as possible. So they get 0.4. So the transfer rate, 0.4 bytes per floating point operation, is quite impressive in terms of a supercomputer. It shows that this machine was really designed to push data around to drive the floating point units. That's one of the strangle points on most computers, is moving the data around. Data movement's very critical, and this machine has a very impressive data movement from memory into the processor. Again, it has a number of things to assist with that. The machine is built from that chip. A couple of chips are put onto a board. They package boards into a shelf. A number of shelves are put together to make up a rack, and then they have a complete system. The system is about 2 tennis courts. Think of it, that's the footprint for the system. It has a peak performance of for 64-bit floating point arithmetic of just under half an exaflop, about 488 petaflops. It can do single precision close to an exaflop, and it can do 16-bit half precision close to 2 exaflops. And that's driving the CPU at 2 gigahertz. And I'll show some examples where that's been pushed to 2.2 gigahertz, where they actually exceed 2 exaflops of performance. So very impressive machine. The Fugaku system is about 19% of all the other machines on the top 500 list, just to put that into perspective. It has quite impressive performance. There's a report, if you're interested in finding out more about the Fugaku, there's a bit.ly link there, bit.ly/Fugaku-report. That's a report that was put together a few months ago, which describes the machine in quite a bit of detail if you're interested in finding out more. This is the #2 machine on the list. It's a machine at Oak Ridge National Lab. It's called Summit. It has a peak performance of about 200 petaflops. It's based on IBM processors and NVIDIA V100 GPUs. And so each node has 2 of these IBM and 6 of these NVIDIA boards. And it's composed of 4,600 of these nodes using Mellanox interconnect. If you take a look at the performance, it's at, so it has the ability to do half precision, 16-bit floating point arithmetic using the NVIDIA boards, and it can achieve 3.3 exaflops of 16-bit floating point arithmetic. Those NVIDIA boards really support some machine learning AI applications. If you take a look at the nodes, 2.3% of the performance comes from the IBM processors and 98% comes from the GPUs. So in order to use this machine effectively, you really must be using those GPUs. And that's sort of one of the downsides, I'll say, of a machine like this. You really have to have a calculation where you can export your floating point arithmetic to the GPU, do it there, and then move it back to the CPU. So there's this constant struggle between the GPU and the CPU of moving data back and forth that has to be maintained. You have to write 2 programs, one for the processor side and one for the GPU side, another complication of this architecture. Where with the Fugaku system, you don't have to do that. That machine has just a CPU, which you program to. It has vector instructions, which are issued to get the performance up. So very different kind of characteristics. The US Department of Energy is engaged in a plan to develop exascale computing. They're deploying high performance computing hardware. They're developing applications. They're developing a software stack that will effectively run on those high performance machines. They're developing 3 systems which should be at exascale. Frontier is the machine that's coming to Oak Ridge National Lab sometime next year. Aurora is a machine developed by IBM that'll be delivered to Argonne at some point. And then El Capitan is a machine that's going to be similar to the Oak Ridge machine that'll be delivered to Lawrence Livermore National Laboratory. So those are the 3 machines. Those machines have a price tag of $1.8 billion for those 3 machines. So about $600 million for each machine at the hardware side. The Department of Energy is also investing about $1.8 billion in applications, algorithms, and software. So the total effort to get the exascale on the DOE side is on the order of $3.6 billion to get there. Quite an impressive outlay, really showing the need for high performance computing to help drive science forward within the Department of Energy. This is again is going to capture some of the trends which are going on here. I've listed here the 3 machines that we've had at Oak Ridge over the past roughly 10 years, I guess. Titan was the first one machine that came in 2012, 27 petaflops. It was replaced by Summit, which was put in place in 2018 at 200 petaflops, the machine I just described. And then Frontier is the machine that's coming in sometime in 2021. 1.8 exaflops is the theoretical peak for that machine, about 100 cabinets. It's going to be based on AMD processors, AMD CPUs plus AMD GPUs, tied together with a high performance link from Cray. Cray slingshot architecture is going to be used to provide the interconnect and a lot of other characteristics there. But it's a GPU-based machine. So again, there's going to be this struggle to move data around between the CPU and the GPU. There's a number of other benchmarks that we have. I'm going to list 2 others. This is the HPCG benchmark. So the HPCG is intended to not stress dense operations. Dense floating point operations like LINPACK are driven by matrix operations. This benchmark is driven by a sparse matrix computation, an iterative method, in fact, to compute the solution to large-scale systems of equations. Many of the problems that are solved on the DOE machines arise from trying to solve partial differential equations. So a discretization is done for that partial differential equations, and that discretization gives rise to a large sparse matrix that's going to be solved. So that matrix problem is quite different than the dense problem, and the performance characteristics are going to be quite different. So we wanted to have a benchmark that would fit into this space. So the benchmark that we have has a results which looks like this. So the Fujitsu machine is ranked the highest for this benchmark. This again is using the whole machine. It was able to run the benchmark, and in this case here, it ran the benchmark with 16 petaflops was the results. So you notice the difference here. You doing the Linpack benchmark, it ran at 442 petaflops. HPCG runs at 16 petaflops. So we have a situation where we're getting much less of the theoretical peak performance. In fact, the fraction we achieve here is about 3% of the theoretical peak performance for the HPCG benchmark. 3% seems quite low, but it is quite impressive given the overall architectures that we're going to look at here. So the number 2 machine is the Summit machine. That was also the number 2 on the top 500 list. They've achieved 2.9 petaflops for this benchmark. Again, a drop to a fraction of 1.5% of the theoretical peak performance. The number 3 machine is the number 3 machine on the top 500 list as well. And you see the performance there. I'm not going to go through all of these, but you can just examine the performance here and see that for this benchmark, we're achieving very little, let's say, a fraction of the theoretical peak performance, but there are some quite impressive machines here. So the Fujitsu machine, the Fugaku machine, and also this other machine based on that same processor that's run at the Japanese Aerospace Exploration Agency is another machine which uses that ARM processor. And again, it achieves about 3% of the theoretical peak performance. Again, this is resulting from using a very simple architecture in some sense, not accelerated by GPUs, but being driven by a processor which was really designed to do scientific computations. Let me just go on to the next slide here. So now we're looking at the peak performance. That's the black line, if you will. The green dots are showing us the performance for the HPL, the Linpack benchmark. So you see it's very close to the theoretical peak. And then this is showing us the performance for the HPCG benchmark. So quite a big drop in performance and going from one to the other. I want to quickly talk about another benchmark that we have. This is a benchmark that really stresses or uses half precision, 16-bit floating point operations. This is a big deal today. It's being used by many of the GPUs to help with machine learning applications. And 16-bit floating point operations, there's a representation. IEEE has a representation for 16-bit floating point. 5 bits are used for the exponent, 10 bits for the fraction. That limits the exponent to a very narrow range, which is potentially a problem. Google has another representation which they initiated called bfloat. Bfloat has 8 bits for the exponents. They have a greater exponent, greater dynamic range, but they have less fractions, 7 bits for the fraction. So that's going to have some impact in terms of the accuracy that we can get out of these chips. So those are the 2 main architectures that we have at 16-bit floating point. We have a benchmark called HPAI, which utilizes that 16-bit arithmetic. And the benchmark goes as follows. It's going to generate a random system of equations, which is diagonally dominant. So we don't need pivoting. So we're going to represent this matrix. So it's initially starts out at 64 bits. We do a casting to get 16 to get to 16 bits. So the matrix is now represented as a 16-bit floating point matrix. We do a factorization of that matrix using Gaussian elimination without pivoting, since the matrix is diagonally dominant. In low precision, we compute the solution at that low precision. So we have an approximation to the solution, and then we perform a few iterations of GMRes. GMRes is usually thought of as a method used for solving large sparse matrix problems, but we're going to use it here to solve a dense matrix problem. I have an approximate solution which I computed using 16-bit arithmetic, and I have a preconditioner. The LU factors are going to be the preconditioner for GMRes. It's a pretty good preconditioner at 16-bit accuracy. And now I go into a regime where I do 64-bit arithmetic. The 64-bit arithmetic is going to be driving the GMRes using that lower precision preconditioner along with that first guess at 16 bits. And it only takes a few iterations of GMRes to get the accuracy back to the full accuracy of 64-bit computations. So we're going to be using 16-bit arithmetic to do the bulk of the computations here in lower precision, order n cubed operations, and then use GMRes to drive the solution O of n squared operations to get back to 64-bit accuracy in this particular context. And that's what we have. We compute the performance as if we had done the whole computation using the original algorithm. So the rate of execution that we're going to be looking at is going to be based on 2/3 n cubed operations over the time to solve the problem. So here's what we get for that. So in a recent run on the Fugaku system, they solved a matrix of order 17 million. So matrix of order 17 million, doing the 16-bit factorization, running on the whole machine, using all of the processors on it. They achieved just over 2 exaflops with a cycle time of 2.2 gigahertz on their processor. They overclocked it to get that. And in comparison, the top 500 number was at 442. So we get about a factor of 4.5 over the double precision, solving a similar kind of problem using that 16-bit arithmetic, 65 gigawatts, 65 gigaflops per watt, the same accuracy as if they had done the full 64-bit precision, but just taking 4.5 times the time it would have been for that. So we have a number of machines which are reporting on this HPL AI benchmark. The Fugaku system is number 1 at 2 exaflops. We ran the same thing on the Summit supercomputer. It achieved about 1/2 an exaflop. On the Selene, this NVIDIA-based system, about 1/4 of an exaflop. On the Joule system, about 1/8 of an exaflop. Sorry, about 1/4 of an exaflop. And then a machine in Nagoya based on this also ARM processor achieved about 0.03 exaflops. So you see the speed up there over the HPL benchmark being driven by 16-bit arithmetic. So I think this is a time when some scientific computations could use 16-bit operations to help drive the performance for their computations. It has to be used selectively. We have to understand what the limitations are. It can't be used for every problem. The condition number of the matrix in this particular case is something that comes into play. The matrix can't be too ill-conditioned, otherwise we won't get any accuracy out of the problem to begin with. Okay, so in conclusion, it's an exciting time to be involved in high-performance computing. A lot of changes taking place. We've seen a lot of changes in the last decade, and looking forward, there's going to be a lot of changes that'll take place in the near future, getting to exaflop. But it's important to remember that it's not about the hardware. There has to be a balance here between hardware, algorithms, applications, and the software that drives that ecosystem. And we can't let that get out of balance, otherwise it'll be too much. So with that, I'm going to conclude. My group at the University of Tennessee is hiring, so if you have anybody interested in a job, we'd be happy to talk to them. And now I'd like to ask if there are any questions.
Thank you very much, Jack. So for the attendees, if anyone has a question, please just use the Q&A feature of the Zoom client, and we will ask the questions for you.
I see we have 53 people on the Zoom session here. So the question is, am I going to post this? And yes, I will post the slides on my webpage. So I'm going to make up a name now. It'll be bit.ly /SC20 UTK Jack. That'll be the name of the thing, all lowercase. That'll be the name of the thing that you could look for. So are there any new systems planned that will be similar to the Fugaku system? No accelerators in the US or elsewhere? So I think the answer is going to be yes. So Cray is actually marketing a machine based on the Fujitsu ARM processor. So you can buy a machine here in the US. A number of people have actually bought the machine. I think our colleagues at SUNY Stony Brook have a machine like this, Robert Harrison. And I know that the guys at Sandia National Lab are acquiring a machine. So it's an architecture which I think is very impressive. They did a very good job of building the chip. It has a very balanced flavor between data movement and floating point. And my guess is a lot of people would be interested in that architecture. So the answer is yes, we'll see that in the US. Let's see, Alexei, my colleague in Ireland is asking, does 16-bit energy efficiency, how does the 16-bit energy efficiency compare? Yes, so the efficiency, let's see if it's included. I don't think it was included in my slide, but the answer is yes. So the energy itself is, well, you can think of it like this. You're going to do 16-bit floating point. So it's faster, so you can solve the problem faster. So at a very coarse level, the LINPACK benchmark, if I was thinking about it, I solved it 4.5 times faster. So in terms of the energy used, I'm going to consume less energy because I can solve the problem faster. How much less? 4.5 times less energy. So so there's clearly a market difference in terms of the energy associated with solving the problem, just coming from the speed of solving the problem itself. Now, the other aspect is, do I actually, when I power up the chip to do 16-bit arithmetic, am I spending less power to do the 16-bit operations than I am doing the 64-bit? And I guess I don't know the answer to that. And somebody's asking here, it says, does power consumption play a role on these systems? Well, power is an important aspect. So think of it in this context. In the US, if I was going to be using 1 megawatt for 1 year, I would get a bill for $1 million. That's what 1 megawatt year costs. You know, we have machines now, the Fugaku system is at 30 megawatts. So I'd be paying $30 million just to turn that machine on for 1 year. So, you know, it's an expensive proposition. So it does play an important role. We want to get that as low as possible. Doing so will save us a lot of money. It says there's a typo, Celine, on the green 500, it says 23. Yeah, I'll have to check into that. There probably is a typo there. Thank you for pointing that out. It says HPL have different algorithms, but change the 16-bit speed up. So HPL was not memory bound, but computational bound. So they're both computational bound. Both algorithms do LU decomposition. So LU decomposition is characterized by doing, you have a matrix, so that's n squared pieces of data, and you're going to be doing n cubed operations. Both are driven by that ratio. N squared data, n cubed floating point. So that's a good ratio, by the way. So I move some data and I do a lot of operations on it. So I get a lot of reuse of data. That's what we want. That's a good thing. So both of those things are characterized by that. In the case of the HPAI benchmark, it's 16-bit arithmetic that we're stressing in that case. And yeah, so let's see. HPL AI is HPC driving AI. AI is driving. It comes from procurement. So which way around is it? Does HPC drive AI? AI driving HPC? So I have to say that so AI is going to be an important thing. So just go back one step. High performance computing is driving, is what's behind simulation today. And simulation is the way in which science is done. Science is driven by simulation. High performance computing is driving that simulation. Artificial intelligence, machine learning is going to be used more and more. We're seeing it being deployed in many scientific applications to help reduce the computational load. Machine learning can be used to get a good first start in terms of where we want to go with the solution. So machine learning is going to be used to help with that. So it's going to be a tool that computational scientists use at every, my view is that is going to be true in many areas of scientific computing. We're going to be using machine learning to help drive the simulation to get to a solution faster. So machine learning is going to be an important, critical component of solving these problems in the future. So that was from Hatem. So Hatem actually says, comment on HPC in the cloud. So a lot of people are say, well, you know, we don't really need these high performance machines. I can just go out and buy Amazon cloud services to take care of my business. And I think that's true for many applications. You can go out and buy services, and that may be cheaper in some sense for your particular application. But we still need these high performance machines. Science is driven by these machines. These machines are used in some cases to run one application. So one application is going to be put onto the machine and get dedicated service of this architecture. In the case of the Fugaku system, one application would be using all of those 7 million cores, or in the case of the Summit, those 2 million processors. We have applications which do that today. I can't do that in the cloud. So if I'm going to be doing the highest level of computation, if I'm going to be striving to get the greatest fidelity and the greatest resolution in my applications, I really can't rely on the cloud providing those services. So I have to be using these high performance machines. The guys at the top of the list, those top 50 machines, I would say, or the top 20 machines are the ones which are really the big producers in terms of the simulations and the science that takes place. I'm not saying that you can't do the simulations in some of the applications on the other machines. Of course you can, and the cloud can be used to do that. Okay, so any other questions? Well, thanks very much for attending. We had a little over 50 people in on the talk. I'm going to post the slides and they're going to be posted to that web page that I talked about. So Alexi's asking one final question here. 7 million cores, any resilience issues in applications? So that's an important aspect. Today, the major driver for resilience is to do a checkpoint and restart. So we do need a lot of work in applications, trying to understand better how we can make these computations more resilient to failure. So I'll leave it there. Thanks very much, guys. Take care. See you next year.
Thank you, Jack, and hope everyone has a good rest of the conference.
Thanks, Jack. I think that went pretty well.
Okay, bye for now, guys.
Bye-bye.